Hi, my name is Sam Jenkins, and I'm going to be talking on behalf of the T2K collaboration about our latest results on neutrino-nucleus cross-section measurements. So the T2K experiment is a long baseline neutrino oscillation experiment, which is based in Japan, and works by taking a beam of muon neutrinos and sending it 295 kilometers across the country to the Super Kamiokande fire detector, at which point we search for oscillations within the beam. If you'd like to hear more about the oscillation experiment and the recent results from this, then please see Maria Antonova's talk on T2K status and plans. So the muon neutrino beam that we use is generated at the J-Park Accelerator Research Complex by taking a 30 GeV proton beam and colliding this with a graphite target. Using a series of magnetic horns, we're able to select out either positive or negative pions and kaons, which then decay in flight to muon neutrinos or muon antineutrinos. And by changing the sign of the horn polarity, we're able to decide whether we want to run in neutrino or antineutrino mode. The beam itself is actually directed 2.5 degrees off axis away from Super K, and this gives us a narrowband beam which peaks at approximately 600 MeV in neutrino energy. So you can see from the plot on the right here that where the flux peaks at about 600 MeV, this corresponds to maximal oscillation probability at Super K. We also use external data from the Na61 SHINE experiment in order to constrain our proton-carbon cross-sections for flux uncertainty measurements. But why do we actually want to measure neutrino interactions? Well, it's important to remember that the event rate that we measure at the fire detector is actually of the final state after neutrino-nucleus interactions have taken place. And this event rate can be decomposed into the oscillation probability from one neutrino type to another, the flux of the initial neutrinos, the neutrino interaction cross-section, and finally the efficiency of the detector. So if we want to measure the oscillation probability, we have to be able to disentangle the effect of this from that of the cross-section. The difficulty in doing this is further compounded by the facts our near and far detectors have different fluxes, different targets, and different acceptance. The table on the right here shows different sources of systematic uncertainty for a recent oscillation paper, and you can see from this that the leading source of systematic uncertainty comes from flux and cross-section. So it's really important that we work to understand neutrino cross-sections so that we can drive down these uncertainties, particularly as we move forward to future long baseline oscillation experiments where we'll no longer be limited by statistics. Additionally, as well as for inputs to the oscillation analysis, a good reason to measure neutrino interactions is because they're interesting as their own field of study. A quick note on how we do cross-section measurements at T2K. Because we're not able to detect nucleon level processes due to the final state interactions that take place as particles exit the nucleus, and also because of the additional smearing that we gain from detector effects, instead of measuring and reporting our cross-sections in terms of the interaction mode that took place, we instead do it in terms of the final state that we saw within the detector. This is known as the topology. So for example, we might measure charge current interactions where we saw one pion in the final state. In doing this, and not making any assumptions on whether, for example, a CC0 pi signal might be made up of CCQE interactions or 2P2H or CC-res where a pion got absorbed, we're able to avoid a large amount of dependency on the generator models that we use for these interactions. 280 meters downstream from the beam production point at T2K, we have the near detector complex, and this complex is made up of several different near detectors which sit at different off-axis angles. The near detectors themselves are used to constrain the flux of the beam and also to perform cross-section measurements. And in this case, having them at different off-axis angles is particularly useful because it means they see different peak neutrino energies, as you can see from the histogram on the right here. The first of the detectors that I want to talk about is ND280. ND280 is a 2.5 degree off-axis magnetized tracking detector, and this means it sits at the same off-axis angle that Super-K does. In the main tracking portion of the detector, this is made up of several subdetectors, the first of which are the time projection chambers, or TPCs in orange. These are gaseous tracking detectors which provide us with particle identification and charged particle momentum estimation from curvature in the magnetic field. The main target mass of ND280 comes from the FGDs in light green. These are both plastic scintillator trackers, where FGD1 is entirely hydrocarbon, but FGD2 is hydrocarbon interleaved with water layers, and this means we're able to perform cross-section measurements on water, which is particularly useful as that's also the target medium for Super-K. We also have a series of other subdetectors, such as the Pi0 detector, the pod, which looks for Pi0 showers in the upstream portion of the detector, as well as the ECALs, which identify showers from electrons and photons and muon range detectors. So ND280 is used to monitor beam composition as well as observing different neutrino interaction rates, and this means we're able to perform neutrino cross-section measurements with it. So this is the setup of ND280 at the moment and has been since T2K started running, but coming up next year we have the ND280 upgrade. And the idea with this is that the pod at the upstream of the detector will be taken out and replaced with several subdetectors, the Super FGD, 2 high-angle TPCs, and then time of flight counters surrounding it. In doing this, we will gain larger angular acceptance, which you can see here, lower tracking thresholds, and in the case of Super FGD, we'll gain 3D tracking from the cube-like structure that is used for the scintillator. So the first measurement that I'm going to talk about from ND280 is that of the nu-mu CC1 pi plus with n protons measurement of transverse kinematic imbalance. So the signal for this is interactions which happen in FGD1, and we look for a single negative muon, positive pion, and any number of protons. Because of detector efficiencies, we do require that those 3 particles exit into the TPC, so there are some phase space constraints placed on this analysis. Once we have these particles, we use the muon, pion, and the highest momentum proton in order to calculate these transverse kinematic imbalance variables. The first of these is the double transverse momentum imbalance, which is done by taking the vector of the muon momentum and using this to form a plane. We then project the pion and proton momentums onto that plane and look at the difference between them, which gives you delta PTT. Relevant to this analysis are also 2 of the single transverse variables, the first of which is the transverse boosting angle, delta alpha t. With no final state interactions, we would expect this to be flat across the full range between 0 and 180. But we find that FSI creates a peak close to 180, and therefore this gives us sensitivity to those effects. We also look at the initial nucleon momentum, which is reconstructed under certain assumptions, and then by looking at the distributions of that, we see how much those assumptions are correct and look at the FSI and initial Fermi motion that could have caused differences. So looking at the results from this, first in delta PTT and PN, the initial nucleon momentum, we can see that the broadening of these distributions related to FSI and initial nucleon motion shows quite interesting model preferences. In particular, we see that the more simplistic relative Fermi gas and local Fermi gas models in blue and red here are disfavored by the data. If we instead look at delta alpha t, which we see here, there's actually less sensitivity from the data here. It shows a mostly flat line, whereas with FSI effects, we would expect it to peak towards 180. But this mostly comes from the fact that we have to place some quite harsh phase space constraints on the proton, and therefore many FSI events become lost. But moving forward to the ND280 upgrades, with the higher angular acceptance and better tracking, we're hopeful that delta alpha T will become a crucial probe for FSI effects. Looking instead at the electron neutrino measurements, in our muon neutrino and anti-muon neutrino fluxes, you can see here the beam has an intrinsic irreducible contamination from both electron neutrinos and electron antineutrinos, which come from the decays of K mesons and muons in the beam. This is expected to cause a large amount of uncertainty for future measurements of delta Cp. So again, it's important to try and understand the cross-section of this. This measurement is performed using 3 signal samples, the first of which is done in neutrino mode, looking at the electron neutrino signal, whereas the other 2 are performed in antineutrino mode, where we look for the wrong sign contamination from electron neutrinos and the contamination from electron antineutrinos. The kinematics for this selection are shown here in terms of the electron and positron momentum, and you can see that a major background of this comes from the yellow part of the histogram, which is a background from photons from pi0 production. But this is constrained using dedicated control samples in the FIT. Looking at the results that come from this, again, the measurements are slightly limited by detector acceptance. So you can see the range of the kinematics that we're able to make measurements over here. The results do show some amount of separation, where the data shows kind of best acceptance for the Newton-Gini models here, but because of statistical issues, we can't fully rule out anything. Although this measurement is limited by statistics, it's still very exciting because it's the first Newey bar measurement that was performed in over 40 years. And again, looking forward to ND280 upgrades, we expect to have much better electron and photon separation due to the super FGD. So really, from this point on, things can only get better. Instead, looking at one of the different off-axis detectors, we have the Wagashi detector, and here I'm going to just describe the commissioning setup that was first used for measurements. So Wagashi is a 1.5 degree off-axis detector, so this means that the flux peaks slightly higher at a neutrino energy of roughly 0.86 GeV. The commissioning setup was composed of initially Wagashi itself. So Wagashi is a primarily water target, which is contained within a 3D plastic scintillator grid structure, which gives good tracking capabilities. Behind Wagashi was one of the off-axis INGRID modules. INGRID is the on-axis detector but has arms that extend to off-axis angles, and is composed of alternating lead and scintillator. So this gives good muon range measurements and tracking. In front of the Wagashi module was the proton module, which initially was part of INGRID, but also got moved off-axis. And this gives us a fully hydrocarbon target, which gives good tracking for both muons and protons. So this is the commissioning setup. The full setup, which is shown here, and includes the baby mine detector for magnetized tracking and wall MRDs, has been in place since 2019, and results will be coming from that soon. So the first cross-section measurement that was made with the Wagashi commissioning setup was that of muon antineutrino and the combination of muon antineutrino and muon neutrino CC0 pi 0 proton cross-sections on both water and hydrocarbon. You can see from the results here that the data has quite good agreement with the Newt expectation, which is shown in the purple dashed line, and the chi-squared values for the fits are shown in the table down here. So as a summary, there's been a continued output of neutrino cross-section measurements from the T2K collaboration, some of it which are novel measurements which provide new sensitivity to model differences, and therefore we really need to work closely with theorists in order to continue to improve predictions. The ND280 upgrade will be arriving next year, so we have exciting potential for new measurements coming with that, but also a whole host of measurements are currently in the works with the current ND280 setup, so please watch this space. I'll leave you with a list of the most recent publications on neutrino cross-sections from T2K. Thank you for listening, and if you have any questions, please either contact me from my email address or in the discussion sessions. Thank you.